Yeah, hi everyone. My name is Tamia Bowers, and I'll be presenting for Team 11 on today. We focused on the study of titanium carbide under space flight conditions. So essentially, the main focus and motivation for our research was centered around 2D materials, which are essentially a diverse set of nanostructured amorphous materials, generally composed of a single layer of atoms. Their applications include energy harvesting, composite materials, and supercapacitors. However, NASA has taken interest in promoting their use in the space program. Recently, a promising new subset of 2D materials has gained attention as a frontier for material science called Mexines. Mexines are notably composed of multiple stacked layers of atoms, therefore creating a 3D material system, and they're characterized by their ability to absorb energy, their high electrical conductivity, crystalline structure, and versatility. Now, with the introduction of such a highly versatile material, presents the opportunity to expand our understanding of working with this material to benefit the future of spaceflight. However, there's virtually no research conducted that can aid in this integration to actual space use. Now, in order to understand a bit more about our research, I'm going to go back and discuss more about what Mexines are. Now, we start off with the max phase elements, and through synthesis, we're able to etch out the A layer of atoms from our sample, therefore leaving us with the equation for our Mexines, in which this blue layer here is representative of our M metal. The gray layer is representative of carbon or nitrogen. And lastly, our surface terminal layer is represented on the surface of our structure in yellow. Now, with our research, we hope to study how spaceflight conditions actually affect the mechanical and chemical properties of Mexines. Firstly, hydration, which has shown to be an important aspect of Mexine synthesis and function, as illustrated here. These accordion hydrophilic-like structures are layered Mexines that are able to swell and expand when interacting with water, thereby affecting the structure and functioning of the sample. In our background research, we found that studies on cement hydration in microgravity display that hydration in space produced larger, more rigid crystal microstructures compared to hydration on Earth alone. Therefore, we wanted to examine hydration of Mexines in this microgravity setting as well. In addition to that, we wanted to examine the effects of electromagnetic absorption, in which these sandwich-like layers are also able to absorb and store energy between them. And lastly, in our microgravity rearrangements, in which we hypothesized that hydration will become more uniform due to the slower movement of molecules in this setting. So we expect to see less hydration heterogeneity and a more ordered structure. And here, this diagram basically just outlines our proposed FME, in which volume 1 is water, and volume 2 and 3 are our proposed Mexine samples. And for the purposes of this, it's important to note that volume 3 will act as our internal control, so it's not necessarily going to be interacted with during the experimentation process. Now in our experimentation, we begin by synthesizing our sample of Mexine, which we have designated as titanium carbide due to it being the most commonly used Mexine sample. This process includes etching the sample in acid to remove the A group elements, washing to remove excess acid, followed by drying the resultant to achieve a dehydrated powder. In our next phase, which takes place on the ISS, we remove clamp A of our FME and simply shake it to mix the water with titanium carbide powder and rehydrate our sample. This proportion is also replicated in a lab on UMBC campus as our ground controlled elements. And lastly, in our analysis, upon return to our lab, we plan to utilize X-ray diffraction to examine the crystallographic structure, SEM coupled with EDS imaging to produce topological elemental maps, and TEM imaging to observe interior structure and analyze our sample. So in essence, the impact and the scope of our research is vast. With the opportunity to basically pioneer research in Mexines usage in space, we have the potential not only to gain a deeper understanding of how to use and integrate Mexines, but eventually expand our limits of space travel, garnering longer space missions, further travel and exploration. And with this, that would go into developing sustainable energy systems and highly efficient batteries. Thank you.